right, so this was the second most confusing topic for students. So I'm just going to do, this is going to be quicker than the last one. A few problems on titrations, okay? So when you're titrating, remember the purpose of this is you're either figuring out the concentration of the substance in the burette, and that's if you know the amount that you have in the Erlenmeyer. More commonly, though, you're figuring out the concentration of the Erlenmeyer flask. What is the concentration of this acid when you're adding a known amount of base, or you're adding a known amount of whatever's in the burette? So in this case, a few small drops are left in the burette that is used to titrate a base into an acid to determine the concentration of the acid. So in this case, I'm determining the concentration of this acid down here. Okay, I know the concentration of this. Will this small amount of water have any effect on the determined concentration of the acid? So if I didn't dry my burette and there's extra droplets in that, and then I add a known concentration of base, will my known concentration of base be the same anymore? No, because I'm watering it down. So what that's going to do is it's going to lower the concentration of my known concentration of base. So that means it's going to take more base to get to the equivalence point. So if it takes more base to get to the equivalence point, what's going to happen to the concentration of the acid? It's going to appear higher than it should. So yes, even though a small amount of water was left in the burette, this would cause an error because it would lower the concentration of base, diluting it, meaning it will take more base to neutralize the acid, making the acid appear stronger than it is. All right, what about looking at it in a different way? So here I have a known concentration of acid. Okay, here I have a known concentration of acid. Well, excuse me. Here I have a known concentration of base and an unknown concentration of acid. Okay, I measured 25 milliliters of this unknown concentration of acid, and I pour it into my Erlenmeyer flask. But that Erlenmeyer flask had some water in it. Now, is that going to affect your concentration of the acid? Now, this one's a little trickier because it's not. Why? Because when you reach the equivalence point, remember, the equivalence point is when moles of acid equals moles of base. So the moles are equal to one another. The moles of your titrant equals your titrant. Okay, whatever you're titrating with. Okay, so these two are equal. Well, when I add this in, am I changing the moles in this acid at all? No. Yeah, you're changing the volume, you're changing the concentration, but I already determined the volume before I poured it into the Erlenmeyer flask. Okay, so if I started with 25 milliliters of this unknown acid and then I poured it into a wet Erlenmeyer flask, that doesn't matter because I'm still going to calculate or use this 25 milliliters that I determined before in my calculation. So the common confusing part students get here is, well, why did it affect the last one? It affected the last one because it changed the concentration of my known. I'm using that concentration, I'm using that molarity of my known to do a calculation. I'm not using the concentration of this. I'm determining the concentration of this using the volume, which I determined before I poured it into my wet Erlenmeyer flask. So in this case, it would not affect my data because I'm determining the concentration, and that small amount of water doesn't change the amount of moles that I have in this Erlenmeyer flask. And that amount of moles that I have in the Erlenmeyer flask is what I'm determining at the equivalence point. And how do I do that? Well, let's do a couple problems just to remind yourself on how to do that. So vinegar. To determine the acetic acid in vinegar, I use a known concentration of sodium hydroxide, 0.55 molarity sodium hydroxide. And to reach that equivalence point, it takes 22.7 milliliters. In my 15 to get to my equivalence point, I measured 15 milliliters of vinegar, and then I poured it into an Erlenmeyer flask. If that Erlenmeyer flask was wet, it doesn't matter. I still had 15 milliliters of vinegar. Okay, so here, what I did was I figured out how many moles it took to get to the equivalence point. Now remember, if my burette was wet, it would take more because my concentration would no longer be valid, because that concentration is very specific. Okay, if I put it into a wet burette, it's no longer the actual concentration that I determined. So that's going to mess up your calculation. But anyway, back to how do I solve these problems? I figure out how many moles of sodium hydroxide it takes to get to my equivalence point. In this case, it's a 1-to-1 ratio, so that tells me how many moles of acetic acid are at my equivalence point. To determine the concentration, I divide by the volume, and there we go. Okay. Couple more titration problems. Here's another titration problem, but here I'm titrating a solid. Okay, so here in my flask I have a solid, and I'm determining the concentration of the sodium hydroxide. So here I'm kind of working backwards. Okay, so I start with 0.1082 grams of KHP in my Erlenmeyer flask. Okay, and to reach the same number of moles of acid that there are in this 0.102 grams of KHP, it takes 34.67 milliliters of sodium hydroxide. This is commonly done to figure out the exact concentration of your sodium hydroxide. And we did this at the beginning of the year. So I figure out how many moles of acid I have in my Erlenmeyer flask, and that's going to equal my moles of base at my equivalence point. To determine the concentration of base, it would be my moles of base divided by my volume of base, and there would be my concentration of base. So what I did here was I determined the concentration of the sodium hydroxide in the burette using a solid amount of KHP. I think just a couple more. All right, a titration where I'm not looking at acids and bases, but I'm looking at a precipitate forming. All right, 50 milliliters of a sample of silver ions of unknown concentration is titrated with sodium chloride until an indicator tells me I've reached the equivalence point. It turns from bright yellow to peach, so it doesn't need to be just acid-base. The chemist initially read the burette to have an initial volume of 0.85 milliliters, and at the end it was 31.5. So how much did I add? I would find the difference there, and it's 25.65 milliliters. What was the concentration of the silver ions in the original sample? All right, so it looks like my concentration of the sodium chloride was 0.185, so there's going to be my moles. That's going to get me to moles of chlorine, which at the equivalence point is going to equal moles of silver. To get the concentration, I divide by my volume, and voila. Another titration problem where it's not an acid-base problem. Okay, a lot of these are 1-to-1 ratios. I would expect that, but you may also have a 1-to-2 ratio, so be careful of that. In this case, it's a 1-to-1. Okay, here's a 1-to-2 ratio. So hopefully we can. So here we can look at an example of that. So here it takes 38 milliliters of 0.75 molarity sodium hydroxide to completely neutralize 155 milliliters of sulfuric acid. What is the concentration of H2SO4? So I'm doing the same thing I've always done. I'm figuring out moles that it would take at equilibrium to get to equilibrium. But in this case, remember, that's a 1-to-2 ratio because it takes 2 moles of NaOH to neutralize 1 mole of H2SO4. So that's going to change my ratio from 1-to-1 to 2-to-1. So that's how many moles of H2SO4 I have at equilibrium. I'm going to divide that by my volume to get my concentration of H2SO4 at equilibrium. Here's a good example of not a 1-to-1 ratio. I should have lines here, and I'm sorry they're not there. Okay? But same problems that we've been doing, except instead of a 1-to-1 ratio, it's a 1-to-2 ratio. All right, and there's some examples of titrations. So hopefully this helped you practice a few more titration problems if that's what you wanted. I'll see you soon.